In this lesson, you learn about managing configuration settings for your application by using a configuration file. Configuration settings include any values that must be set before an application can run correctly. These values can include hardware configuration, file paths, default UI values, default state data, and other values that you may want to initialize. Depending on the value, you may only need to set configuration settings once, or you may need to change the value based on state changes or user input. If you only need to read configuration values once, you might use constants on the block diagram to set them either outside of a loop or inside the initialized state. This approach has the benefits of being quick and easy to implement. It also abstracts those values away from the end user. On the downside, this static approach runs into challenges if you come back later and need to modify the constant values. For example, later on you might need to use different hardware or want to log to a different file. If you set the values in multiple locations based on different states, then you will have to change the values in each location. If you want to change the value while the code is running, you will have to stop the application, change the constant value, and then rerun the code. For some configuration values, you might want the user to set the values before running the VI, or allow the user to change them while the code is running. To do this, you can create controls on the front panel. This approach has the benefit of being dynamic and enabling the user to change the configuration values while the VI is running. On the downside, this approach can result in a very cluttered UI, depending on the number of settings and controls that you use. Additionally, since you're allowing the user to modify these settings, there's a risk of the user entering incorrect values. As an alternative to using block diagram constants or front panel controls, you can use a file to store configuration settings. This file can serve as a single location to set and modify all of the configuration settings for your application. If you need to update values between executions, you can modify the file instead of searching for constant values on the block diagram. By defining these values in a file, you can ensure that any settings that are dependent on each other are loaded together, reducing the chance of user error. If a value is used in more than one location in your application, you can read the value twice, eliminating the risk of changing a value in one location but forgetting to change it in another. An additional benefit to reading configuration data from a file is that you can easily switch between different configuration files. Each file can contain all of the appropriate settings for a given scenario or hardware setup. You can create one file that contains the default values for the application and use a file path control or file dialog box to enable the end user to choose a different file. File formats that can store configuration data include delimited files and .ini files. A delimited file is a text file that uses some special character to separate columns of data. A tab delimited file uses tabs to separate data, and typically has a .txt file extension. A common separated file uses commas to separate data, and typically has a txt or CSV file extension. Loading configuration data. Use the delimited spreadsheet VIs to communicate with the delimited file. To store configuration data, you could use a single write delimited spreadsheet VI with a 2D array of strings to write the configuration data to a delimited file. In this example, a tab constant is wired to the delimiter input of the write delimited spreadsheet VI. Loading configuration data from a file can have its challenges. After reading the file using the read delimited spreadsheet VI, you must first index the resulting 2D array before you can extract the information you want. After you extract that information, you must convert it to the appropriate data type. If you update the second row of this file with a new piece of information, How would you need to update the VI? If you want to search the 2D string array for the value of a specific configuration setting, also known as a key, you can search for the row in column 0 containing the key name, and then return the corresponding key value from column 1. For example, suppose you want to know the value of sample rate. In this VI, the index array function returns all the key names from column 0, and then searches for the key name sample rate using the search 1D array function. This function finds the key name in row 2. Next, the index array function returns the value from row 2, column 1. In this example, the key value of 1000 is returned. A tab or comma delimited file enables you to store configuration data for later extraction and use in your application. This approach has the benefit of being relatively easy to write and read the file contents. The downside is that this approach requires you to develop custom code to extract specific values from the file. The data will be read as a string, so you will need to convert it if you need to use it as a numeric. If you don't know the specific row or column for the value, you must implement custom code to search the 2D string array. Initialization, or INI files, use a predefined format to store values. To create, read, or modify an INI file, use the VIs found in the configuration file palette. An INI file has a defined structure. A section is a group of related configuration settings, otherwise known as keys. This INI file has an analog input section and an analog output section. Here we see the keys in the INI file. Each key has a name and a value. In this INI file there are 4 keys. The key named samples per channel has a value of 1000. This example VI writes one key value to an INI file using the write key VI. In order to write a value to an INI file, you must specify the section, the key, and the value you want to write. The write key VI will automatically adapt based on the data type of the value input wire. In this example, the write key VI adapts when a DBL data type is wired to its value input, and then provides additional precision and format inputs. You're able to specify the format and precision to determine how to format the DBL into a string to write to the INI file. The code to read data from an INI file is very similar to the code that you used to write the data to the file, except we'll use the read key VI. For each key value that you want to read, you must first specify the section that you want to read the value from, and then the key name that you want to read. The read key VI reads a value associated with a key in a specified section in the INI configuration file. If the key does not exist, the VI returns the default value for the value output and returns false for the found output. In the polymorphic VI selector, you can configure the data type for the returned key value. In this example, the read key VI is configured to return a DBL data type. You use INI files to store and load configuration data for your application. The benefit of this approach is that it's easy to write and read configuration settings and organize them into sections. The write key and read key VIs have built-in data type conversion and configuration settings. The downside of this approach is that you are required to use one write key VI for every key you want to write, and one read key VI for every key you want to read. So if you need to write or read multiple keys, you need to use multiple write key VIs and read key VIs. Let's take a look at an example of loading and storing configuration in an INI file. First, let's take a look at the write config data VI. This VI starts by generating a file path and sending it to the open config data VI. Then we have a separate write key VI for each key to write to file. For each write key VI, we specify the section, key name, and key value. The write key VI will automatically adapt based on the data type of the value input wire. For example, the string input here made this one a write key VI string. The DBL input here made this one a write key VI DBL, which provides additional precision and format inputs. The I32 input here made this one a write key VI I32. Lastly, we use a close config data VI to close the file. Running this VI will generate this INI file. Now let's take a look at the read config data VI. We pass each read key VI a section and the key name, and the read key VI returns the key value. Notice that I can select the polymorphic VI selector and specify the data type for the returned key value. We'll use this as a sub-VI to read configuration values in an application. When used as a sub-VI, the configuration file path will be an input and the returned key values will be outputs. This application starts with the initialize state, which checks if there is a default .ini file in the same directory as the .lv project file. If so, it uses the read config data sub-VI to return all the configuration values from the ini file, which then are stored in this shift register. So now all states have access to the configuration values. If a default .ini file does not exist, the application will just use its own default configuration values from this initialize shift register constant. When running this application, if the user clicks the Select Config File button, the application will go to the Select Config File Value Changed event case, which gives the user a file dialog box to choose an INI file. Then it reads the configuration values from the INI file and stores those values in the shift register. Here's a summary of what you've learned in this lesson.